Alright, here is the promised follow-up video for the power bank. The original power bank video, by the way, here's the power bank. I will talk about this whole setup in a minute. But yeah, the original power bank video got a ton of views, well, at least for my channel size. And it got featured here and there. I heard from a friend that it was on Dangerous Prototypes. By the way, the sole comment on that Dangerous Prototypes blog was kind of funny. The general consensus I got from this and personal comments, people like it, and a lot of people seem to be asking, where can I buy this? At the end of this video, I will be talking about how you can buy this. You cannot buy it yet. I'm thinking of crowdfunding a bunch so I can get manufacturing costs down and get it onto a somewhat reasonable price, but still kind of expensive. So if you're still interested now, please watch until the end of the video or skip to the end of the video. There's an annotation here. But regardless, really what this follow-up video is about is looking at the performance of the power bank and looking at how everything is doing. And for that, as you have been able to stare at for a while now, I have my thermal camera, my Seek thermal camera, on the computer via a little program you can find on the EEV blog forums called Seekofix, which has the will inset the thermal camera frame here, and you can see if I move my hand around here, it's pretty blue. I put the temperature range from 25 to 100 degrees, where 25 degrees is pretty much black and 100 degrees is white, and in between you get the rainbow colors, so you can really see when things get hot. Now, in order to feed the power bank is currently full, and as you can see there, my lab power supply is continually supplying the power bank with power. That is not just to make sure that the batteries are full and that the performance is maximal, but also because the charger actually produces its own heat, which we'll be able to see. And the charger is currently set to 1 amp, and we'll be able to kind of extrapolate whether charging at 3 amps will work or will thermally overload the board, because there's a lot of stuff going on at once. Now, in order to load down the power bank, we have my setup for my PSU power bench setup. The fans will not be running, the power is way too low for that. But yeah, this is the same that I used in previous builds. I will someday come back to this and make an actual product out of it, something that looks nice, but right now it's just like a crappy little custom board and lots of switch resistors and a current measurement board here. Now, before we actually start testing, let me just run you through the layout of this board. So here we have the power inputs. Here we have the main on-off MOSFET switch. This is controlled by both the actual on switch and a little voltage monitor here that forces the unit off when the battery voltage becomes too low. That's the under voltage protection. Then here we have the charging circuit. This is the actual chip. This is the inductor. We expect both of these to get pretty hot when it's charging at 3 amps, but I won't be charging at that rate today. Then we have the main body of the power converter. This is the inductor. This is the controller chip. This is the MOSFET, and these two are the output diodes. And this is going to be, I think, the most fun part, because here you have an actual discrete implementation of a boost converter. So the inductor, the controller, the MOSFET, and the diodes, they're all separate things. And you'll be able to see different things heat up as the output power becomes higher. So first, you will probably see, I haven't actually tried this yet, so this is all kind of conjecture. Usually you see the diodes heat up first, while of course the controller chip itself will be dissipating power even if the output is pretty much unloaded. But then the diodes will heat up because they have a fixed voltage drop. They have a relatively high loss at low output current. As the current increases, you probably expect the MOSFET to heat up. And then as the current becomes really high, the inductor will also increase its power consumption. You will see this one heat up more than the MOSFET. So I think that's the order in which things will be competing for the highest temperature spot. Now, besides that, so this produces 12 volts on the output. Then we also have the 5 volt output, so the output to the USB ports, and that's done by this TPS61030. This is a fully integrated DC-DC converter, very much like the battery charger, which is also fully integrated. So that means it's just a chip and the external inductor. And you basically expect this chip to become pretty hot as it approaches the maximum output current. All right, so here we are at the test bench, and here on the top left we have the voltage. It looks very jagged, looks like it's varying a lot, but it's actually only varying between 12.089 and 12.099 volts. I'm sorry about the font size. You'll probably not be able to read this. That's all right. This is not actually meant for showing on YouTube videos. On the bottom left, we have the current, and on the right, we have power. So what we'll be looking at, I will actually show you. When I press on the plus here on the hamburger, the power will go up, the voltage will probably sag a little bit, and the current will go up. And what we really want to see is we want as little voltage sag as possible. We want these steps to be nice and clear, and we want the power to basically stay constant. We don't want things to look like they're going up or down a lot, because that would mean the converter is unstable. Okay, sorry about the cut here, but I had to adjust some windows back and forth. It might look a little bit different. I zeroed the output, and the first thing we can see on the thermal image, as it has, I think this has been running for about 15 minutes now, it's been on for a while, and you can see that on the top left of the thermal image, there's a little like blue square where it's slightly warmer than the rest. That's the on LED. It's not actually hot, it's not actually a higher temperature, but I think the thermal sensor is a little bit sensitive to the radiation coming from that LED. Not 100% sure why it's doing that. And on the bottom right, you can see the actual controller chip for the DC to DC converter, which is slightly warm, but nothing interesting. It's like 30, 32 degrees right now. So we'll increase the power. We'll go to 1 watt. Let's see. Oh, I actually overshot. It's 1.4 watts now. Well, that's fine. 1.4 watts, and very, very slowly you should be able to see some of the components' outlines appearing in the thermal image. So you can actually now see the MOSFET being like registering at all, and the inductor is heating up very, very, very slightly as well. So this is not very interesting to look at. Let's just go to 10 watts. Or, you know, we're at 7. Yeah, there we go. 9.4, 6, 7, 8, 9. 9.9 watts, that's fine. So now we're at 10 watts output. And oh, that was cool. Did you see behind those wires running off the board? Suddenly the charger chip kicked in, and yes, it's now actually charging at 1 amp. And the charger chip is now also about 35 degrees. And this is also, I just love power converters. I do this for a living, so it's good that I love it. You can see the diodes heating up. You can just see that it's two diodes, and those are currently the main heat source for the power converter. And also, this is pretty funny. You can see, because there's a big ground plane on the PCB, you see the entire board heating up, actually. The entire board is getting a slightly brighter hue of blue. So, still the controller chip is clearly the warmest thing, and there's basically no loss in this entire converter right now. I've done the calculations on this, and it should be in the neighborhood of 96% efficient at this output, which is, I think, pretty awesome for something that runs off of 4 volts. But let's increase the power. Let's go to 1.5 amps. Let's go to 18 watts. Ooh, slightly overshot. 18.4 watts. There we go. Things are really really heating up now, and we still see that the main dissipating component in the power converter is the diode, but there's another component that is slowly heating up at the same time, and that's the main on MOSFET on the left side of the PCB. You still see that the converter MOSFET is slightly warmer. It's just ever so slightly brighter green right now. But the on MOSFET is also dissipating power. And this, I found out the hard way when I was just testing myself using the device and just probing it with a Type K thermocouple. I noticed that under maximum load, when I was charging my tablet with it, that MOSFET got so warm it was like hot to the touch. I couldn't keep my finger on it. And that shouldn't happen. So in the next revision, definitely one of the improvements will be replacing that MOSFET with a lower resistance one. I think what's going on here is that the voltage that I'm putting on it, the source gate voltage, it's just ever so slightly too low, so it's not fully on. So I need something with a lower threshold voltage. Anyway, things have heated up quite significantly now, and we can see that the controller, the MOSFET, and still the diodes mainly are getting into the upper green range, which I think is 45 degrees ish. And we can see that, yeah, well, the diodes still dominate, but other components are definitely heating up now. So let's increase power. Let's go to 2 amps. Let's go to 24 watts. 25. 25 is fine. And yeah, things are definitely heating up here. We're getting just in the yellow range. You can see like a speckly yellow blob on the diode and the MOSFET. And that's a good 55 degrees there. Also, yeah, that on MOSFET on the left side is definitely heating up. I am losing a lot of power here. There's something else I should tell you about this. You will see pretty high temperatures. I think we might even get over 100 degrees. We'll see if we load it up fully. And this is still by design. This doesn't mean that the board will get too hot when it's in the enclosure, because there is just too much heat. There's no active cooling. There's not even thermal transfer to the case right now. These very small components, they will dissipate power. Even if this converter is ridiculously efficient at maximum output power. A reminder, if this is outputting 36 watts, that means that if it's running from 4 volts or maybe even 3.5 volts, the input current is going to be 15 or more amps. So this thing will get definitely very hot, even at 90% efficiency. It will have to dissipate a couple of watts, which is too much for these components just in free air. So you really need a thermal pad between the board and the actual case, the aluminum case, to be able to run this at higher power output for a long amount of time. But in the voltage and current graphs, we see that it's still holding strong at 12.05 volts, and we don't see any deterioration in performance. So let's go up. Shall we go to full power? I don't see why not. Let's see what it can do. And here, yeah, things are really heating up big time. We are pretty much at full power here. Let me just pull 3 amps. Yeah, you can see that the main MOSFET and also the on MOSFET are at about 100 degrees right now. And this is too hot. Funny enough, now you can see the power just ever so slightly sagging, and you see a lot of power transfer, or I should say a lot of heat transfer. I'm actually going to reduce the power output. Yeah, there we go. It was going down slightly already. You could see the graph kind of sagging. So it really doesn't have enough heat transfer to the surrounding air right now to be able to sustain the power output. And you could see, maybe I should reduce the power a lot to make stuff cool off. And yeah, you could see that the actual components that are the hottest are the inductor, which is still very hot. Also, of course, due to the amount of mass that it has. It just takes longer to cool. But the other component that was definitely heating up the most was the MOSFET. Well, actually at 10 watts, that's a little bit low. Let me just go to a respectable 20, 25 watts, somewhere at that vicinity. So you could see that it was really the MOSFET and the inductor that were now dominating power dissipation, and the diodes, which were dominating before, they've cooled off significantly. So yeah, I just love looking at these kinds of thermal images. It's awesome. But very clearly, both the inductor and the MOSFET, I think, are ever so slightly undersized for this application. At lower input voltages, the inductor will have to conduct even more current, and the MOSFET obviously as well. And those will probably exceed 120 degrees on the board, even in the enclosure with a thermal pad underneath. So I'm hesitant, as the board is right now, to call this a 12 volt 3 amp or 36 watt output power bank. I think it would be more honest to say its continuous output rating should be about 2.5 amps. So let's say 30 watts. Because yeah, if I put it, I'm at 29.5 watts now. That MOSFET is still getting in the vicinity of 100 degrees. If it's going into white, it's over 90 degrees. So that's still pretty hot, pretty excessive for long time use. So in the next revision, I will be replacing the MOSFETs. I will try to look for a better fit inductor, not 100% sure. And I will try to tweak it a little bit more to get slightly higher efficiency and to make an easier mounting for that thermal pad to the case, so that it can actually lose its heat to the casing. Now, last thing I would like to show you is something I didn't put any attention on. But of course we have a couple of big capacitors, and these are polymer capacitors. But it's interesting to see, even though they are very, very close to this inductor, which is a large heat source, physically large heat source, you can see the round thing on the thermal image. It's cool. It's green. Yeah, It's getting up to like 40 degrees, but that's all right. And the only red you can see on the side of it, that's actually a reflection. It's the aluminum of the can reflecting the heat, and that's actually coming from the inductor back to the thermal camera. So I'm very happy with the thermal layout of the board itself. Apparently it's all right to put this polar capacitor, if it's not touching it, to put it still relatively close, as long as there's just air in between, which doesn't conduct heat very well. All right, let's zero this, and let's change over the, I love looking at this type of thermal imagery. Let's switch over to, oh, we had a little bit of an overshoot there. That's interesting. I'll have to look at the compensation circuit to make sure that this doesn't happen too badly. It was only 0.15 volts overshoot, but still, that's fairly egregious. Let's take a look at the 5-volt converter and see how much it heats up under load. Right here, I've connected the load bank to the 5-volt output, and I've let the main converter cool off for a little bit, but it's still a little bit warm. You can see the inductor is still very clearly visible. And something I forgot to mention in the previous clip, you couldn't actually see when the big converter was outputting max power and going at 30-35 watts, you couldn't actually see the charging circuit heating up. Besides it was really the power dissipation on the entire board was dominated by the big converter. And that means that definitely the charging circuit can handle much more current. It can easily handle 3 amps. So I'm very happy with that. That means that that's probably not been under-designed. However, we really want to be looking at the 5 volts. And as you've been probably seeing for a while now, it looks like it's has a lot of ripple on the output. And the ripple is a fairly low frequency. The fact that this power bank can see it means that it's only a couple of hertz. However, it doesn't look like it's much. If I go to the long integration period, the voltage RMS ripple is only 23 millivolts. So it looks like it's a lot, but that's just because this is the vertical axis on the voltage plot is just very zoomed in. So anyway, let's increase power, and yeah, right away, even though we're just drawing 8 milliamps, which is nothing, it's already completely stabilized. So it's really just a no load phenomenon. With 8 milliamps, it's already a very quiet supply with, let's see, 800 microvolts of RMS output ripple. It's actually very good. All right. You still can't really see it on the thermal image. Now that the rest is cooled off, you can kind of see the outlines of the components better. It's not just one big glowing blob, but on the far bottom right of the PCB on the thermal image, you should start seeing things heat up, but we are at 250 milliwatts, so I don't expect any significant power loss to be there yet. Let's go to a watt. Yeah, nothing really happening. I'm a bit impatient. Let's just go to a full amp. Well, actually, the voltage is sagging a little bit. It's at 4.92 volts now. I think that's my cable. I don't think that's the converter, because the converter is probably pretty solid. I will check that later. Because it is kind of a flimsy power cable. I should have gotten a different one. Yeah, it's definitely not in regulation. If it were at 4.9 volts now, that's pretty bad. Well, anyway. Uh, we were going to 1 amp. Takes a long time. There we go, 1 amp. We see the chip, the TPS 61030. It is kind of heating up a little bit. It's in the 40-degree range, well, 35-ish. Nothing really interesting, honestly. The output is, or at least I designed it to service up to 2.5 amps with 2.1 amp per output. So really, what you can do is you can charge one fast charging device, and then you can charge a small device like my headphones, for instance. They only draw 250 milliamps when they're charging. Yeah, let's just go on. Yeah, the voltage is sagging a lot. We'll just look at the amps then. I would whip out my multimeter right now and see what the voltage drop over the cable is, but that would disturb the test setup. So here we are at 1.7 amps. So that's a good, well, that would be about that's not too far off the mark. That would be about 8.5, 9 watts. And it's clearly heating up. We're at the 55, 60 degree mark. Let's just go up a little bit more. Let's go up to 2 amps. Let's fine tune it at 2 amps. Good enough. 2.006 amps. And yeah, it's definitely the chip itself that is heating up a lot. You get that with these integrated drivers, but it's still reasonably fine. You would expect this. We're very close to the maximum rating of the output. We're only rated to 2.5 amps. So I guess what we get from this the most is just looking at a crappy cable. Get good cables, people, if you want to use fast charging. All right, let's just load it up fully. See how far it goes. Heating up to a good 80, 75, 80 degrees. And now it is starting to sag, is it? Yeah, it is. See? The voltage is definitely trending down. No. Stabilizing slightly. Still getting more current from it. Getting more power. Usually when yeah, there we go. When it's really at the end, at its maximum, when you increase the current, the power doesn't actually go up. And yeah, here we go. We're at the maximum, and the power is sagging a lot. So it's only doing 2.4 amps, really. I'm not too stoked about that. That means that I have to look into improving my, well, really changing the entire chip to something else in order to deliver that. That's a bummer. I would have hoped for this to output more than 2.5 amps. And as it is right now, it only seems to be capable of delivering, well, let's say 2.1 amps at the full input voltage range. So, yeah, too bad. Better luck next time, I guess. Maybe I should have built another discrete boost converter for that as well to really get some output grunt. Oh, things cool down so quickly on these boards. I love looking at this. All right, so the last thing we would really like to know about this is what is the efficiency and what is the actual capacity that you can get out of it, because so many of these power banks, they say they're 10,000 milliamp hours, but if you have a 2000 milliamp hour if you have a 2000 milliamp hour phone, for instance, you won't be able to charge it 5 times fully from that power bank, simply because there's converter losses. And you could see here, like this main converter, it gets really hot. There is 3, 4, maybe 5 watts of power dissipation in there, because it's going to be only 85 or maybe 90% efficient. All the rest, all that charge which was in the batteries, it just goes to waste as heat. And the same goes for the 5-volt output. And this is honestly not a very bad converter for 5 volts. This is like one of the higher efficiency models that TI has. So imagine in like these big power banks that do get a little bit hot when you charge your phone with it. There's quite a lot of energy being lost here. So I would really like to see the efficiency. However, this video is running long, and I would like to talk about a possible crowdfunding campaign for this as well. All right, so I've had a lot of people asking about where I can buy this, and my previous answer was it's not really for sale. I made 10. I made 11 and I sold 11. One to myself and the rest to people at the hackerspace, RevSpace. And that was basically it. It was really made for 2 people, me and a fellow hacker named Sebastius. Me for my Cube i7, and for Sebastius it's his Surface Pro 4. Both of them require 12 volts to charge, and there are no really good power banks for that. So I sold them. Full disclosure, sold them for 50 euros. And that is, it's not quite at a loss, but the amount of time I spent on these, I definitely didn't get back. Fully assembled, everything, all the components, tacks, enclosure, printing the thing, the batteries, obviously. It costs about 45 euros. If I would do a Kickstarter, I would have to significantly up the volume. I would have to make at least 100 to make it worth my while, because then I can reduce the my costs to maybe around, well, I guess still about 45 euros, but then yeah, I would have other costs. I would have Kickstarter fees and that kind of stuff, so it doesn't really get much better. And then I would have to sell them at a minimum 80 euros, possibly even 100, because again, I have to pay 20% VAT. I have to make sure that I can replace them if people receive a broken unit. There's time in it, so it's gonna be basically just keep in mind the number. It's gonna be $100. Now I'm interested. Are people interested in a 12-volt 3-amp power bank for $100? There are some more interesting things. The next revision that I'm making will have a microcontroller built in, and you will be able to interface that microcontroller via USB. It's going to have an AVRX Mega with USB, running like a virtual serial stack, and you will be able to program the battery charger and use this thing to charge any type of battery, even if you want like LFPs or like FIPOs, whatever you call them, the non-explodey type batteries, or you can build your own giant battery bank with other things. You can even charge lead acid if you want. And the other thing that would make this interesting is, obviously I've made this to fit the case, and this exactly fits 1, 2, 3, 4 18650s. But there's nothing stopping me from making a bigger butt and throwing in an extra cell, or 2 extra cells, or 5 extra cells, or using longer extrusions. I can probably get longer types of extrusions of this, and sell power banks with higher capacity, more or less to order. Also, the microcontroller that I'm putting in here will be doing current measurement. So you will be able to do very crude lab supply type stuff. Oh, I forgot to tell you, the output will have a digital potentiometer, which can change the output. It's in fairly large steps. You can change it by, I think, 0.3 or 0.4 volts at a time, from about 10 to about 24 volts. So you'll be able to output any voltage you like. Obviously, the efficiency is going to suffer at the high end, so you won't be able to output the full 36 watts at 24 volts, I don't think, but I'll have to test that. Anyway, you will have a programmable output thing with just normal Powerbank functionality. It can be larger or smaller, and it's open source. So with all these things in mind, would you still say, nah, $100 is maybe a bit too expensive for a Kickstarter? I would really like to hear your input on this. If people are positive, if people still like it, I will consider putting out a Kickstarter, and if we actually get to about 100 units, I'll be able to produce this and deliver in a very short amount of time, because it's basically there already. The basic layout, everything works. We just need to look at safety certification and that kind of stuff. It's gonna be an awesome project, so I hope people like it. If not, I am not sure if I want to make more of these. It's a fairly time-intensive process, welding the batteries together, assembling the whole pack, sourcing the materials. There's a lot of different things. Printing these backs, that's also a thing. If I would do a Kickstarter, I'm not sure if I can get away with 3D printed things on like a normal desktop 3D printer. I would have to get something that looks a bit better. I cannot do injection molding, but you know, there are some things that you can do and you cannot do that people expect in an expensive power bank. So I'm not sure if it's worth it if I only make a couple at a time and sell them on my Tindy. So did you like the video? Do you have any comments at all about the Kickstarter or possible Kickstarter? And do you have any comments about the rest of the video? Then I would really like to hear them below. If you don't want to write it in public, you can always send me a DM. See ya!